Okay, so this is the first Griffiths problem for using ladder operators for simple harmonic oscillators. So in the section 2.3.1, we went over how you apply ladder operators for a simple harmonic oscillator. And now we're going to be solving some problems using ladder operators. Okay, so first off, this problem, I want to point out some things about it first. So the most important thing of any problem is to actually read it. So the goal here, because it's very easy to lose track of your goal when you go through a whole bunch of work. So the goal here is to show that the lowering operator, that's A minus, and just as a reminder, we have A plus, A minus, those equal 1 over square root 2m. We have h bar over I d dx, plus or minus, depending on if it's the raising or the lowering operator. And then we'll have I m omega x. So the lowering operator lowers it one rung down that energy ladder. So we have an energy ladder. If I apply A plus, my energy goes up a level. If I apply A minus, it goes down an energy level. If I'm in ground state energy, psi naught, ground state, I can't go any lower. So if I try to apply the lowering operator to it, I can't go any lower because I have a finite bottom of my energy well. Since my energy well has an energy landscape that has a minimum, that means I can't have an energy below that minimum. The way that I've defined my oscillator to have like your typical spring potential, 1/2 k x squared, where yeah, we could solve that for k. Let's just leave it like that for now. Anyway, what we have is x squared there. So we have a parabola, meaning we cannot have a negative energy. So what we're trying to show here is that if we apply the lowering operator to the ground state and try to normalize that solution, this guy, so if I try to normalize the solution here, I do not get a valid answer. Can't be normalized. This is what we're trying to show. So if psi is a normalized solution, then we want to know what happens. I guess I sort of gave away the answer. We want to know what happens if I try to apply the lowering operator to a normalized solution in the ground state. So what we're looking at here is the fact that if we have a wave function that satisfies the Schrödinger equation, then we have a normalizable solution. So that means that if we have some solution psi n, it's normalized, so that if I integrate that over all space, psi n squared, I can normalize that to equal 1. Every state is normalizable, so I could apply a raising operator to it, and I could apply a lowering operator to it. They do not have the same normalization constants, however, But what I do know is that this state is normalizable. And in general, I know that this state is normalizable, except if my in was equal to 0. Oops, squared. So that's where we're starting from. This is what we want to show. That because this wave function is normalizable, that means if I use a raising operator to go up an energy level, then that solution is also normalizable, which means that this should equal a constant. That's what our goal is to show in general. So then we can apply the same logic to our ground state wave function. And then we will see whether or not applying the lowering operator to the ground state wave function is valid or not. Does that give us a normalizable solution? So basically, is there an energy state possible with any probability of finding it that is lower than ground state energy? So, spoiler, the answer is no, but we have to prove it. Now, before I begin, I'm going to point out this guy, because I think a lot of people are going to be tempted to just go, one, if you're familiar with dirac notation, say, oh, it's easy to do in dirac notation. That's not the point of the problem. The point of the problem is to actually show it, not to just declare that the raising operator and lowering operator are Hermitian conjugates of one another. That's not the point. The point is to show how it works. So we will not be doing that. I think that's a little bit too hand-wavy and missing the point. Because if you don't show all the work explicitly, then that definitely weakens your argument about the energy level below the ground state being normalizable solution or not. Just my personal opinion. If you want to use dirac notation and just declare that they're Hermitian conjugates, go ahead. But I think that's a little bit too hand-wavy and not the point. So we're going to be doing it this way. So once you get this, by the way, getting this is pretty easy. That's why there's, a lot of hand-wavy about this part. But it's not that hard to just show it. So first what we're going to do is going to start here. And we'll start with the we're just going to do the lowering operator. Okay, so from negative infinity to positive infinity, what I know is that this should give me some constant. So I want to know what that gives me. Now that's going to equal the complex conjugate of the lowering operator and psi n times the lowering operator times psi, acting on psi n. Let's go ahead and work out that complex conjugate of the lowering operator. So that's going to have a 1 over square root of 2m. Suppose I should make that a little bit more clear, instead of trying to jam it in there. Now for the complex conjugate, we just take all the imaginary parts and we're going to change their sign. So this is going to be, getting ahead of myself. This is our lowering operator. but I want it to be the complex conjugate. So I'm going to change the signs of the imaginary parts. That means changing the sign of both. I will give you a fair warning here. If I were grading this and you just declared that the lowering operator is the complex conjugate of the raising operator, I would not be put in a good disposition to give you points. And the last thing you want to do is not put your grader in a good mood. I'm going to go ahead and pull this complex conjugate through. So what I have here is, since I have a function, the complex conjugate of psi naught, my operator has a thing to act on. So my operator is acting on this complex conjugate, psi naught, or psi n. I'm going to go ahead and just pull through the other guy too. Why not? So let's go ahead and just put everything together. So I have the derivative with respect to x that's acting on the complex conjugate. It's not acting on the other part because it already acted on the complex conjugate. And then this part, we just literally pull it through. Now I'm putting this lowering operator times psi n in parentheses because I'm going to be treating those like as a pair. They're buddies and they are going to stay together for the rest of the solution. Now I'm going to go ahead and split this into two integrals because I only want to do integration of parts on the first one. So to make this clear, I'm going to just go ahead and I'm just going to keep the constants in here because why not? So I'm going to have this integral. This is the one that I want to do integration of parts on. So I'm going to go ahead and explicitly break this up because I don't have any sort of math pride in this. I don't have a stake in this fight. I would rather show, like, to myself, I would rather be careful in making sure that I'm multiplying my constant all the way through. So I'm going to be explicit writing it out because I don't care if somebody says, oh, it's super obvious that you can just keep the constant out and throw it out there and just do the integration parts quick and dirty on this part, that the only part that really matters. I don't have any sort of pride like that. I would rather keep it straight because I don't want to mess up. So, second integral I don't really need to do anything with. I'm just going to keep it there so I know it's there. The first one I want to do integration of parts on. So I want to define which one I want to have as my u, which one I want to have as my v. So I'm going to call this lowering operator acting on psi in my u because I would rather differentiate it than integrate it. Integrating it isn't going to get me anywhere, so I'm going to have du, and that's just going to be dx of that function. My v, I'm going to throw the constants in here. Like I said, I really don't care that they're there. I would rather keep this all straight than mess up. And my v is going to be this guy integrated. So my dv is just the same constants. And that's going to be dx of psi n. So we will be doing our integration of parts. We defined our u and our dv. So I have dv and I have u. And that's going to equal the integral evaluated minus the integral of v du. So now I'm going to have the integral evaluated of u times v. So let's just throw these guys out in front. So here's my v. My operator has something to act on, so I'm good and happy there. And that's evaluated at negative infinity and plus infinity. Then we're going to be minus our integral here, which is going to be dx, and here's our constants, which has a negative sign. I'm going to throw it out there. Right, we had a negative sign there. This is where, if you said that the lowering operator was just a complex conjugate of the raising operator, no, because that would mess up your solution. And then we had our, so that's v, and then du was dx here. And then we had our second integral, which we didn't do anything to, but I'm just going to pull it down. Okay, now here, this one, here we want to actually look, what is psi n? Psi n is an, so some normalization constant, times a ladder operator acting in number of times to get it up to energy state n, times our psi naught, our ground state, which is this exponential. If I evaluate that at positive infinity or negative infinity, so as my limit goes to plus or minus infinity, what I have is e to the negative plus or minus infinity squared. So that's always going to be e to the negative infinity, which is going to go to 0. So I can flat out get rid of that first one. And now I just have the two integrals. I'm going to go ahead and roll them into one again. Now the first one, I get a positive sign. So I have dx. I have 1 over square root 2m. That's by both of them, right? Oh, you know, I wrote the sign wrong there. There we go. That was a plus, so it's a plus. So I have square root of 2m times h bar over I psi n complex conjugate ddx of lowering ladder operator on psi n, and then that's plus I m omega x psi n squared acting on, and then lowering operator acting on psi n. Okay, so from here you can probably see how we got our solution. Well, let's go ahead and pull these out here. So I'm going to go ahead and pull out the psi n's because there's nothing acting on them. And then I have 1 over square root 2m h bar over I ddx. And I'm going to go ahead and pull these guys out and put them over here because the operator is acting on them. So that's why I need to put them on that side. And it's acting on this as a whole because lowering operator and psi n are buddies right now. So this guy you'll notice now it is my raising operator. Oops, with the constant too. So what I have is now complex conjugate of the wave function times raising operator, lowering operator, and psi n. Zero hand waviness in there at all. I am not a big fan of solutions that are designed to make the person providing the solution look smart instead of actually explaining the solution. So now we can use, this is the result that we had in a earlier section about our raising operators and lowering operators and how they commute. So this is equation, I think 2.46. There we go. So we're going to use equation 2.46. I'm also going to use equation 2.50. So we already used part of it. Now I'm going to use the second part of it. So now let's go ahead and work that out. We have a plus a minus psi n. That's going to equal En times psi minus 1/2 h bar omega psi n. Let's go ahead and put that in this result here. So I'm going to be replacing that. I have complex conjugate psi n. I have En psi n minus 1/2 h bar omega psi n. Now I'm going to use this result from equation 2.50. So that means that my En is n h bar omega plus 1/2 h bar omega. So we're going to go ahead and put that into here. So that's psi n complex conjugate n h bar omega plus 1/2 h bar omega. Oh, whoops. I needed to factor out that psi n. And then minus 1/2 h bar omega, and then times psi n. These two cancel each other out. And then what we're going to be left with, let's go ahead and make sure we pull up our problem so we don't forget what we were doing. So what I'm left with here, although actually I think I did the one for raising operator, didn't I? Let's double check. E minus h bar omega. We did lowering operator squared, making sure I didn't make a sign mistake here. Oh, I just went one step too far. Let's stick with this one. So let's start with that on the next page. So what we have here, we could put it in terms of in, but this, see, that's what happens when you forget what you're doing. So we have psi n complex conjugate, and we'll just keep it with En minus h bar omega psi n. And now, since this doesn't depend on x, because we know that E is just n plus 1/2 times h bar omega, meaning there is no x dependence there. So I can just pull that out completely. Or if you want to get fancy with it, you could just say that's in h bar omega. And then what we're left with here is just our integral of absolute value of psi squared. But we know that this has to be a normalizable solution, so that's 1. So what we have is, going back to our very first equation, we started with this, and now we know that it equals E minus h bar omega. Or, by the way, in h bar omega. Okay, so E n, that is the energy state for psi n. Now we want to know what happens if we apply that to the ground state. So now we're going to replace psi n with 0. So basically n equals 0. So one thing, if you kept it this way, you'll notice right away what that integral is going to equal. But let's go ahead and show it. I think that's why they didn't go that far with this hint here. So now we're going to have negative infinity to positive infinity. I'm going to have lowering operator acting on psi naught. That's psi naught squared. That equals E naught minus 1/2 h bar omega. Now E naught is just 1/2 h bar omega. We did this also in the section 2.3.1. So what we know here, we also know is that our lowering operator acting on the lowest rung of our energy ladder takes us to 0. So that means lowering operator acting on psi naught is 0. And now we have 1/2 h bar omega minus 1/2 h bar omega, which is also 0. Now, the integral of 0 is a constant. So this is my justification for why you needed to show all that work, because I know it'd be tempting to go, well, duh, it was just the integral of 0. Well, the integral of 0 is a constant. So's this. So's in the energy state. It's at least constant with time. So just showing that this was equal to 0 and you're taking the integral of 0 doesn't show anything. That would be the same as any normalizable state. That also equals a constant. But in this case, the constant is 0. So that's why we had to show that it was equal to the energy level minus 1/2 h bar omega, or show that it was equal to n times h bar omega. So what that means, like what this literally translates to, is 0 probability to find it in that state. So there's 0 probability to find it in a state lower than the ground state. If I apply the lowering operator to my ground state wave function, I now have a 0 probability of finding it anywhere in space. So it is basically not normalizable. So normalizable would mean it would be equal to a constant, and I could, just put, I could put any normalization constant I want in front of it to normalize it to 100% probability. But if my entire integral equals 0, I can't multiply anything by 0 and get not 0. So that's our final answer, that what this tells us is, in the case of psi equal to ground state wave function, we cannot get a normalizable solution by integrating the absolute value of the lowering operator acting on the wave function squared. Okay, and we'll be using a lot of the same technique for the next problem. We will also be using integration by parts to manipulate that, even though it's very similar to what we just did. We'll just be doing it for both the raising and the lowering operators. And again, not using dirac notation, not because dirac notation isn't good, it's just that it's not the point of the problem.